Okay, welcome everyone to Lecture 8 of 5828, Foundations of Software Engineering. Apologies for running just a little bit behind today. Okay, so we're going to finish off the last little bit of Lecture 7 that I couldn't quite get done last time, and then dive into our material today, which is Lecture 8, Introduction to Concurrent Software Systems. And that'll set us up for the next, we have 4 more weeks of material before we get to the midterm. This is the end of week 4. The midterm is going to be Tuesday of week 9. So that gives me about 8 lectures to play around with. And what I'm planning on doing is probably getting through the material in chapters 2 and 3 of your concurrency textbook. And then more material on the Agile lifecycle. I haven't had a chance to really look at it yet to see how much of the Agile textbook we'll be targeting. But most likely we'll have, with those 8 lectures, about 4 of them on concurrency and 3 or 4 on the Agile methods, and that'll take us up to the midterm. So that's the overall structure there. And before I dive in, is there anyone who has questions on homework 2? Yes.
Suppose commit 7 is the most recent commit of a branch. What's the difference between checking out that branch name versus checking out the hash of commit 7?
Checking out the branch name tells, yes, the question is, you have a branch, and commit 7 is the most recent commit on that branch. What is the difference between checking out the commit itself, so typing in the hash and hitting return, or checking out the branch name? And I think, but I don't know if this is exactly correct, but I'd have to go check. But checking out the hash directly puts you in a detached head state where Git will want you to tell it which branch you're on so that you can then make more commits. If you were to, in a detached head state, so that means that the head is no longer associated with a branch, it's now associated with a particular commit. If I remember right, in a detached head state, if you start to make commits, Git doesn't know where to put them. And so those commits can be lost or difficult to recover or integrate back in again. So if you recall with the, in the example that I did, we did a bunch of commits, 0, 1, 2, and 3. And then I jumped back to commit 0. And then the first thing I did was create a branch. And then that told Git, okay, the next commit goes on that branch. So if you check out the branch, then it says, okay, go to the latest one of the branch, and any subsequent commit goes on the branch. So that, I believe, is the difference.
And then one follow-up. If you're in a detached head state on that commit 7, and you merge another branch, like a bug fix branch, normally if you're on the commit and you merge, it'll be the commit. The branch will be the one that you were on when you merged. But if you're in a detached head and you merge, does it then become the new branch?
So this question is, if you're in a detached head state and you do a merge, what happens? My firm answer on that is I don't know. My guess would be that Git might warn you and say, I don't know where to put these commits. That would be my guess. So we'd have to check on that.
Thank you.
Any other questions? So this will be my last reminder. Make sure you do quiz 1 before Saturday. I might actually on Friday post and say on the website, don't forget about quiz 1. It's open until 11. I think it's open until 11 or 11:30 on Saturday night. Do not email me on Sunday and say, would you reopen the quiz? I won't. All right, any questions on that? Okay.
So for presentations,
yes.
Do we need to be like? Do you need to be seeing like commits about once a week or twice a week or something like that for checkpoints?
Right. That's up to you. So I haven't asked you to share those repositories with me yet. What I'll be doing when you do share them is I'll go and at some point when I review the presentations, I'll go and see what was the commit history like. Did they start late and have lots of intense activity? Was it a long, what was the style in creating the presentation? So for your own, my own recommendation for your own work style is to work a little bit and commit as you're making progress.
Okay.
But that's not something I would mandate. Although I did indicate before, don't give me a repo that has one commit with everything showing up in that one commit. I don't want to see that. But there's otherwise no requirements on that. But it is kind of what's nice about it is it does reveal your history to you yourself. Oh, how did I work on this thing? Oh, look, bunched it here, long break in the middle, bunched it there, that kind of thing. Okay, so let's go back and finish off Lecture 7 because I really want to get to Lecture 8 and get it done today. So we were at the very end of this lecture looking at some of the roles that people play in agile life cycles.
Is the other screen?
Oh, that's interesting. To the studio, Kate Studio, this monitor appears to be off. Could you see if you can turn that on? But for now, we'll use this one. Yes, so what we were talking about, so archetypes is just a fancy word for role. And these are the most common roles. Now, not every agile life cycle will have these roles. These are just ones that tend to show up. This one's good. Is it powered on?
It is.
Okay. I am using, so with this one, I'm connecting via the HDMI cable. I'm not connecting via the VGA.
Maybe I can try a different one.
Yeah, okay. All right, so we're working on it. Excuse the technical difficulties. So these are the common roles you might see across agile life cycles: customer, analyst, programmer, tester, project manager, and UX designer. And I gave you these roles right after I said in the lecture series that roles tend to blur in agile projects. You'll be expected to play multiple roles, but these are the kind of the primary jobs you might see on a day-to-day basis. And whether you step into it or someone else does, these are tasks and responsibilities that someone's going to have to deal with. So the agile customer serves as ground truth for the requirements captured in the user stories. So when you have a user story and it says the customer wants, or the system shall do X, well, that's because the customer told us, and so we're going to trust the customer. Great, let's see how this one goes. Thanks. The customer told us that this is what they want, and so we take that as truth. If the customer changes their mind, well, we have a new truth. And if there's ever any ambiguity, it's the customer that goes and resolves that ambiguity. Let's see what we got here. Nope, no signal on this one now, on any of the monitors. So we have to swipe. Top, that's what it says there. Let's see. Let me try one more time. That might have done it. This one's on now. Yay! Okay. All right. So, and as I've emphasized multiple times in this particular set of slides, the person who's acting as ground truth is also one of the people who will use the system being developed, and that we want to have them be invested in what's being produced. So they want to be able to volunteer their time, because if they get the requirements delivered to you correctly, then you're going to start producing a system that they want to see, and they have a lot of power. They'll discover that they have a lot of power in the direction the team goes by saying what the next story is and what the priorities are. So we got through this. So they set the requirements, so they determine what gets built. They set the priorities, so they determine what gets built first. And they're the ones who determine what stories get dropped if the team is running out of time and or money. So usually you have fixed constraints on time and money. So when you've run out and something went wrong, and the difference between the waterfall model and the agile model is that in the agile model, your customer's been there with every decision along the way. And so now when it truly is time is running out or money is running out, they will have known the story as opposed to having to go to some external customer that was disengaged and have to go explain to them why now we're not going to make what we promised. But so that they're the ones that say, okay, well, here's what we were aiming for. We're not going to quite get there. Out of the stories that are remaining, I can let go of these 5 features. I really need these last 2 high priority features. So they can engage in that conversation. The analyst then is the person that goes and tries to track down all the relevant requirements for a user story. So all the traditional activities associated with requirements, requirements gathering, disambiguating, eliminating ambiguity, doing things like paper prototypes. Is this what you want? Doing storyboards. So the workflow you described, if we have a screen that does this, that goes to this, that goes to that, and then has this loop, is that what you want? Oh, no, it isn't? Okay. And then they've got to be able to step up and do that type of work. They might draw some UML diagrams for the developers to say, out of what I'm learning from the customer, these are the primary concepts. We're going to have to track these particular concepts. So we might put them as classes and go from there. And so this work doesn't disappear. We just distribute it differently across the project, doing it per story as opposed to trying to do it all up front. The programmer then is someone that steps in and takes a user story and typically converts it first to tasks and then takes those tasks and converts it into code. And as all the tasks get finished, the story becomes more and more functional until it's starting to pass its tests that the user wrote and it's ready to roll out. So what the programmer will do, the programmer role will do, is they can help generate estimates for user stories. So this is a new story. How long do we think it's going to take to code? Well, I did one of those just last week. We can copy what I did, and it should go pretty quickly. That's a small story, 2 days, right? Versus, oh, wow, I don't know anything about that class of technology. We probably should spike on the technology first for a week, and then we can estimate, we'll know more, and we can estimate the story then. Those are the types of things that a programmer in Agile setting will do. They will be technically literate. They can make design decisions about what tools and frameworks and architectures might be useful for a particular problem. They will generate test cases, and they will use those tests to move the project forward, keep track of where things are at. They will also look for opportunities to refactor code and look for ways of keeping it extensible, simple, coherent, loosely coupled. And they will work to identify, configure, deploy, and use the tools that the team will need. Things like setting up Slack, making sure everyone has the shared repo, all those kinds of responsibilities. The Agile tester is someone who is a developer, but has decided to focus in this context on ensuring the quality of the overall system via tests. So they'll write test cases for user stories. They'll gather data about the system. They will check things like performance. So I'm jumping here to my bullet here. They will test both the functional and the non-functional aspects of the system. So the functional aspects of the system are what it's supposed to do for the customer. It has feature A and feature B and feature C, and I can get my work done with those features. The non-functional things are like the things I'm listing down below. They're characteristics of the system. How scalable is it? How efficient is it? When the machine that it's running on crashes and the power goes out, how reliable is it? How robust? Does it, is it mess when it comes back up and I've got lots of work to do? Or does it just pick right up where it left off? If you're the latter, you say that's a more robust system than one where you've got to go in and do a bunch of cleanup after a crash. So all those things refer to kind of the non-functional. We call them the ilities oftentimes: security, scalability, reliability, and the like. The project manager then is another role. They're often a team member that is separate from the developers, so they may not be an active contributor in terms of code generation, but they're the one who's keeping track of what stories were assigned to this iteration. Are we making progress? Are we on track to having them done by the time the iteration is complete? If not, what can I do to make sure we get back on track? They will communicate, they'll be responsible for communicating the state of the project to the team, to the customer, and any other relevant stakeholders, other people in management, and the like. They're going to be working to remove obstacles that the team might be facing so that the rest of the team can just focus on the development of the software. And they will be identifying when some plan is not working and lead the team to get back on track. And this might be having conversations with the customer first. Are these priorities set in stone? Can we change a few of these? We're having this problem that's going to delay us. What can we do to get back to a good state? And so this one is more of a traditional management role, much more communication focused and making sure things are running smoothly so the rest of the team can be successful in the iteration. And a UI designer, or user experience designer as they're now called, is someone who focuses on the visual aspects of the system, if that's the type of application that's being generated. I mean, if you're working on back-end server software, there's not much in terms of user experience that you have to worry about, other than making sure your command line flags are standard. But if you've got a graphical-based system or a web-based system, then someone needs to be thinking about the user experience. What are the visual aspects? What are the types of interactions? So user experience is more than just how it looks. It's the workflows that the system offers, the ability to be used on multiple devices. So if I'm out and about with my phone, what can I do with the system versus when I'm at have a laptop with me or I'm at my desk on a desktop? How does the system respond to all of those? What's the overall workflow, and what's the interface for each of the people that are part of the workflow? And there'll be ones that are trying to do things that make the user experience high quality. So I won't talk about it at all in this class. We have a user-centered design class at CU. We also have a rapid prototyping class here at CU. Both of those classes will focus on this aspect of system development, and I recommend them. The human-centered computing faculty trade off on who teaches user-centered design, but that's usually a good project-based class. And rapid prototyping class is taught by Tom Ye, and his philosophy is getting you to build things right away. So he's all project-based and applied learning in his class. So those are good ones to check out. But some of the techniques you'll learn about in user-centered design will be things like usability studies. So this is our interface. This is our workflow. Does it actually work with people who are going to be our users? What does it happen? And one of my fond memories related to software engineering is being at Microsoft and watching a usability test occur. And this was done formal test. There was 2 rooms. One room had the person that was taking the test. The other was the other room was the person who was controlling the test. And there was the usability engineer, and then there was a one-way mirror in between them. So people in the testing room could look at the person who was taking the test. And I kid you not, as this person was stepping through some of the things they could do with this program, and they were basically, the goal of this particular test was, can the user discover the way that the user interface is set up? So they would give them a task. Why don't you go and search for cities that have this true about them? And then that's all they'd be told. And then they've got to figure out from the UI, oh, I could type my query here, or should I browse here? They had to figure out from the UI what would go on. And what was hilarious about this test was within, I'd say, 10 seconds of the test starting, the entire development team was spread out on the window, right? So they couldn't be seen, but they were right there up against the window going, oh, come on, it's easy, it's simple. Like they're rooting for them. And then when the person is clearly confused, they're like, oh, God, back to the drawing board, that kind of thing. So it was actually very, they were right there hoping for success, and it didn't go that well, the one that I saw. But that's what happens there. So you bring the team in, you have them watch an interface that made total sense to you, doesn't make total sense to your customer. Time to go back and figure out what you're going to do next. And so then things you'll encounter there are personas. What are the types of users you want to support? The types of scenarios they're going to be doing. What tasks they're going to be trying to finish. Doing rapid prototypes, bringing that to the user, doing storyboards, etc. These are all sorts of things that you'll do as a UX designer. Okay, so that got us through the roles. We'll be returning to those roles. Like when we look at Scrum, I'll go through the roles that Scrum has designed. And a few others as we move down the line this semester. But in this set of slides, what we looked at was a high-level introduction to Agile methods and the Agile way of thinking about software development. By now, it should be pretty clear that it's very different from the traditional style of software development. And yet, I think it has a style, it has a set of practices that addresses one of the core problems from the traditional life cycles, which was the ability to hide from the fact that you were slipping, that your schedule was slipping. So people in traditional waterfall life cycle models have a great ability to hide the fact that they're not making enough progress. because they're just doing requirements. That's all we have to do is just generate requirements documents, right? And then when you get to design, we're only doing design. There's no coding going on, right? And it's not until you get to the testing phase that, oh, wow, we're really far behind. This is going to take a lot longer than we thought, and, all those kinds of things. And with Agile, you're up front. We have a couple of things that we think we can do in 2 weeks' time, and then there's no hiding from it. If you start to get behind and you're not going to make it by the end of next week, you know. And so then you surface the conversation up front. What are we going to do to get back on track? Can we go talk to the customer and get more time? Those kinds of things. That becomes so much more important and so much more visible in the Agile lifecycle. Okay, so now we're going to switch gears altogether and talk about the other aspect of the class that I wanted to spend a good amount of time this semester looking at, which is how do we design software systems that are concurrent. And so what I'm going to do in this particular, in this lecture is I'm pulling, actually I think I say it here, I'm pulling material from chapter 1 of our textbook, our current concurrency textbook, the 7 concurrency models in 7 weeks book. But I'm also pulling some material from this other book, which I still highly recommend. It came out back in 2012, 2011, and is still really good. Programming Concurrency on the JVM. And I will be, as we go forward, I'll be pulling from both of these books as material on this particular issue. So the question you might ask is, well, why worry about concurrency? Concurrency is hard, but I've only ever needed single-threaded programs in everything I've done ever since I started to become a programmer, so why should I care about it? And in general, that sentence is going to become harder and harder and harder to say with a straight face. Because everything that we have, including our phones these days, ship with multiple cores. And the multiple cores are just sitting there waiting to give you tons of performance if you'll just use them. And if you don't use them, you're not going to get that performance. So the big change in this environment is that there are tons of multi-core computers. It didn't used to be the case that we would say, oh yes, this desktop has 12 cores. Just not the case. Now it has been, and it's been this way for probably 4 to 5 years now. And the other thing that's going on is the use of computing clusters. So you get a bunch of machines together, they become a cluster that operates as one, and then what can you solve with a cluster of computers that you couldn't solve with just a single computer? And cluster computing, you hear the phrase high-performance scientific computing. In terms of, you get massive parallelism, massive distribution. And it used to be that like the machines that had massive parallelism were just single machines that had been architected purposefully to have tons of CPUs. And those were very experimental back in, say, the late 80s and early 90s. And so there was just one machine that you ran parallel software on. Now it's much, much cheaper to buy what they call commodity machines that cost you a couple thousand or even less, and put them in a rack, and suddenly you have, say, 10 nodes, each with 12 cores. That's 120 cores that you can now be executing workloads across to get things done. And in the big data world, where everyone, I never say, I say I work in big data, but I never say how much data I have, because no matter what I say, there's always someone out there that's like operating at 2 orders of magnitude larger than what I am. But places like, Facebook, a couple years ago, said that they generate about 500 terabytes of new data each day. And that was a statistic that they talked about 2 years ago. So I'm sure it's only gone up since then. And so in order to be able to effectively process and index all of that data so that I post something and my friends can find it when they search, you've got to be able to process 500 terabytes of new data very quickly so that the searches are almost real time. You can't do that with single-threaded programs. You can't do that with single machines. You need clusters of machines to be able to do this. So that's one of the reasons why you need to worry about concurrency. You need to be able to write concurrent systems so that you can start to scale up to these larger and larger contexts. And you can't even hide from it for these things. The Android world always likes to say, oh, it's 8 cores now, oh, it's 10 cores now, now it's 16 cores, right? They're always touting the latest phone, which has the most cores. So even our handheld devices have multiple cores on them, and if you truly want to see performant systems on them, you need to be able to take advantage of that as well. The other side of this is that the growth rates for chip speed are flat. I lived during the glorious time where you could wait 18 months and your computer was twice as fast. And now we're on that logarithmic curve where we're starting to flatten out. So you can no longer wait 18 months for a 2 times speed up anymore. Instead, chips are becoming wider. So a single chip will have more cores on it, will have a wider bus, which means it can pass more data at a time, and we'll have more memory on chip. So you have your L3 caches, your L2 caches, the things on chip that can speed up computations. All of these things, we layer abstractions on top of all of this, but it's gotten to the point now where there's so much potential in what's going on in the hardware that that's breaking the abstractions up above, and we have to be able to plan for them. So I just want to give a quick example that I draw from a great book by Big Nerd Ranch called Scattered. And it's a program that just, you point it at a folder of images and it loads up the images. Now, what it does is it will load each particular file and then ask for it to animate. And the animation starts somewhere at the center of the window and then moves the image into place at some random location in the window. Now the problem with the the problem with the single-threaded version of this program, which is sitting over here, let's make sure I'm in the right one, single-threaded. The problem with the single-threaded version is if I run it, it comes up and it says, let me just load it here. So you're preparing to load. Now it says loading, and then it's like nothing happens, and we get the beach ball doom of, the cursor of doom. Oh, and then they all animate at once. So there they all were. It was a whole boatload of images, and they all showed up at once. And it took, in this case, 5 seconds to load that. And that's not what we wanted at all. But for whatever reason, this is what we got. So slow performance and not the right animation that we got. Now, unfortunately, I don't have time to show you the source code and what's going on here. But I can talk at a high level about what's going on. So at a high level, what's going on is that GUI applications, graphical user interface applications, are event-based. And there's almost always a thread that's devoted to just handling the events. So it's called the UI thread or the main thread. And that thread, all it does is it goes to the queue, which has all the events that this particular application is supposed to process, and it reads an event off. And each event has a handler, or it could be that the event doesn't have a handler, and then it doesn't do anything. It just throws it away and gets the next one. But if it has a handler, it calls the handler, and then it waits. Because we're single-threaded. There's just this event, there's just this one UI thread, and it calls the event handler. Now, the assumption is that the event handler will execute quickly. It'll make a small change to the program and return. If you ever get an event where you say, go do your stuff to the handler, and the handler doesn't come back, you're host. Your whole graphical user interface just freezes. You get the spinning beach ball cursor of doom on Mac OS X and similar cursors on other operating systems. So the framework is assuming the event handlers execute quickly. What's happening in this particular application is that after it loads the window and does a little countdown about loading in 2 seconds, once it does the actual load, it calls a event handler that loops through every image in the folder, loads it, and asks it to display itself. Loads it, asks to display, loads and display. The problem is that the event handler is never returning. And so even though it's asking for things to be loaded and asking for things to be displayed, that's just being stuck on the end of the queue with no work actually being done. And while we're in this event handler, the UI is blocked. If I had tried, the cursor of doom actually showed up, I couldn't have, resized the window, I couldn't have dragged it, any of those kinds of things while it was blocked. Our application just becomes non-responsive. So how do we fix the problem? To fix it, there is no simple fix. It becomes a change in design. We had just the wrong design. You can't load and display those images, so many images, in one event handler and expect to have things go nicely. The event handler has to be short. So you have to realize that you have 2 tasks in that workload. One task is loading an image, and one is displaying an image. Now, the displaying an image is something that the UI thread should do. And what you can do is say, hey, here's this image that I have. I'd like you to animate it to this particular position. That's actually an event that the UI thread is supposed to do. So you tack it onto the end of the UI queue, and it'll eventually get to it and cause the animation to happen. What shouldn't happen in the UI thread is I/O, loading files. It shouldn't be doing that. So you have to abstract that task out ask a background thread to do it for you, and then notify you when the image is loaded. And once the image is loaded, then we will, now we have the bits in memory, I can go say animate, and everybody will be happy. So unfortunately, again, I don't have the time to show you this code. It actually is available. I skipped over that right here. I can't distribute the code. This comes from Big Nerd Ranch's book. However, the code is freely available. You can just click this link here if you want to see the source code for this. Okay, so here's the multi-threaded version. After we've done all that work to change the design, let's quit that one. And go to our multi-threaded one and say run. And you'll see almost instantly, after this load thing done, here they come. Right? So all the images can be processed in the background. The UI thread doesn't get blocked at all. And while additional files are being loaded, it's just taking care of the animations that have been requested. And since there were so many files, we could easily, tons of files can be read in the background while we're busy animating the first couple of ones. The other thing to realize is that, human time is not computer time. So there are lots of things it can do in these other threads, which might strike us as being really long, but for it can handle pretty efficiently once it's been broken down into tasks, because those tasks go out to all the cores. This particular laptop has 8 virtual cores, so up to 8 tasks can be running at the same time in it. It has 4 physical cores, but it can simulate up to 8 virtual cores. And so, yeah, the difference is quite apparent. You get the animation you want, and the total time of doing all these, did I get the wrong one? That was the wrong one. That was the single-threaded one. The total time, rather than being about 5 seconds or 7 seconds, is only about 1.5 seconds. But what's more important is your user is happy. They're seeing all these images. Like, they don't even notice how long it's taking. Whereas before, when you had a blank screen, now that seems like eons. What's going on? Yeah?
Why can't you just block? I understand that this is way faster, but why couldn't, in the other code, just block on a single image so that as one image will come up, it'll show that image, and then it'll...
Right, and that's exactly right. That's changing the design. That would probably be the first thing to try, would be to see if that's acceptable. But even then, you are relinquishing your event handler, right? So your event handler says, go load these images. So now you got to figure out, how do I do one of these things at a time? And you have to yield and let the event queue run before you handle the next particular image. So you might still be stuck having to do a background thread, in that. But yeah, the more important thing is that the code becomes, we can handle this, we can solve this. There are known techniques for doing these things, and we'll review them. But the complexity of your code inevitably goes way up, right? Because now you're dealing with threads, who's doing what, what's the task, how am I distributing it, when are these tasks done? I have to be notified now that the file's ready. Now I've got to write an event handler for that notification. There's all sorts of things that you add to the system to make this possible. And so this is where the challenge comes in. So the benefits are that you get great performance that scales with the number of cores. Maybe not linearly, but you get to see nice performance increases over the single-threaded version to 2 cores, 3 cores, 4 cores, and the like. Eventually it does start to level off, and we'll show that. You get responsive applications, especially in the graphical world. People can, if your system is putting long-running tasks in the background, your GUI application stays responsive to what the user is doing. And that leads to happy users. The problems associated with concurrent software systems is that we have to change our way of thinking about our design. The simplest way of designing it with a single-threaded solution that unfortunately, but necessarily, we've been taught since the beginning of our journey as being programmers and software engineers, is not the way that's going to win the day. You have to switch over the way you're thinking about designing these systems to do it. And designing for concurrency is hard, all sorts of perils that we'll discuss next. So with this as context, let me go back to why worry about concurrency. So basically, the other thing to say here is that since chips are not getting faster in the same way they used to, single-threaded, single-process applications will not see any significant performance gains from new hardware. Now, today's machines are plenty fast, so in terms of the performance of that one core, that one single-threaded, versus what I had when I was growing up, night and day, really, really fast. But if you want to see true very impressive performance gains, then you need to say, I got to get away from single-threaded design, and I got to think about how can my application take advantage of multiple threads. And then if you can design it to work in parallel as the number of processors are available to it increases, you can expect the same application to be, somewhat fast on 2 cores, more fast on 4, and way fast on 16, right? So your design goal becomes, how do I make it scale as linearly as possible with the number of cores? And this is not easy, so as we'll see. Fortunately, lots of frameworks are coming out that make it easier than what it used to be. And the first 2 concurrency lectures will be showing you what we used to work with, the very low-level threading APIs, and all the sorts of problems that can creep in from that. And then we'll be starting to see more modern frameworks where a lot of that has been moved around. The key thing, though, is that we need to identify what our tasks are. What is it that can run in parallel? And that is a key design shift. Okay, and I think I've already talked about this. Yeah, so this is where, this is this N-core thing. I've already said most of this. One thing I haven't said yet is that there is an opportunity that's starting to be taken advantage of now that, yes, your machine might have 12 to 16 cores running on it, or for like servers that you put into racks and data centers, those can have 48 cores, 128 cores. They can have a lot of cores. But your graphics card on these machines typically have 1,024 cores on them, 2,048 cores, right? They have huge amounts of parallelism. Now, I say here, granted, those are designed for very specific types of algorithms, but there are actually people out there now that used to be saying, well, you can only use those things on graphic applications, right, to process video, process images. People are working now to try to put a layer of abstraction, right? My very first slide of the semester, all problems can be solved with a layer of indirection, right? People are now working to try to put a layer of abstraction that allows us to program the way we are comfortable with, and behind the scenes, farm it out to these video cards. And then you could be seeing desktop performance where you've got thousands of cores available to your application. And one thing I'll say, last year I saw my first program that runs on these graphics cards. And the interesting thing is that normally when I report how fast something's running this semester, I'll be using milliseconds. When we spent the lecture on the graphics card, the performance was measured in nanoseconds. Right? So it becomes a huge potential speed up if you can get stuff to run on your graphics card. Okay, and I'm going to skip over this slide because I want to get to the meat. So here's, I always have repetition in my lectures. My apologies if that annoys you, but repetition is good. A deep chasm opens before you. To work in this world as a concurrency designer and get everything to work right is a lot of work. And you will make mistakes, and they will be the type of mistakes where you get a bug that shows up once every 100 runs. So really hard to then track down. Or it never appears in your development environment, and you ship it to your users, and it shows up all the time over there. You can get these really subtle timing bugs, what are called race conditions, that are hard to track down. So it is error-prone. And when you're trained for single-threaded programming, these errors, this class of errors is almost completely unfamiliar. The need for synchronization, the fact that if you don't do synchronization, you get into race conditions. And I'll show you some examples of that coming up. Deadlocks, where everything's running, nothing's running. Every thread is blocked. What happened, right? And then these things called memory barriers. I'll show you that in a minute. So let's review some terminology here, just to get everybody on the same page. So when we execute a program, we create a process. And a sequential program will have a single thread of control in that single process. A concurrent program will also run inside of a process, but will have multiple threads of control. And what that means is that it could be calculating or executing code in multiple, well, there's the phrase, thread of control, in the process. More than one thing could be happening at once. And a single computer can have multiple processes running at once. But if that machine has just a single processor, and for the sake of argument, a single core, as they used to be when I was growing up, then the illusion of having multiple processes running at once is just that, an illusion, right? The computer is just so much faster than us that it can run a little bit of this, and a little bit of that, and a little bit of this, and we humans perceive it as both happening at the same time. So there were versions of Mac operating system, version 4, version 3 back then, in the eons of time, where they would, I think it was actually in the name of the Finder, something about multi-finder was what it was called. And it was able to do more than one program at once. And you could actually see the program in the background running while you were in the foreground typing. And I know this doesn't sound cool now, but back then that was amazing. But it was just an illusion. There was only one core. So it was just doing a little bit of work between the two. So this illusion is then maintained by the operating system. The operating system has a scheduler, and it's the one that decides what runs and what runs on the processor or across the set of processors. And with a single processor, there's only one process is running at the time, and the scheduler is just swapping things out to make it all work. But if a machine has more than a single processor, then you go from concurrency, which is simulated parallelism. They look like they're running at the same time, but only one thing's running, to true parallelism, where you have multiple things running at the same time. So you have n processes running simultaneously on a machine that has n processors. So thus, if we go to our Venn diagram, parallelism is a subset of concurrency. So you can have concurrent software systems that are not parallel, right? Or you can also have concurrent software systems that are parallel, truly parallel, and multiple things are happening at once. And it's in this here where you can start to get really big performance increases over single-threaded programs. Now, it is possible to be a concurrent program, but still, what is this? Okay, so be a concurrent program on a multi-core machine, but still just be concurrent, not truly parallel. And so, for instance, there are languages out there, Python and Ruby among them, that have what's called the global interpreter lock. And that global interpreter lock, you can write threaded code. You can write this thread, that thread, this thread, go run. But the global interpreter lock in those interpreters will not allow those threads to run in parallel. And that used to be true of everything, but they've since gotten better. If one of those threads blocks because of I/O, it's waiting for disk to come back to it, it will run another thread. So you get a little bit of parallelism, but not true parallelism in those situations. So you can have a concurrent program on a single core machine, you can have a concurrent program on a multi-core machine, and depending on the runtime environment, it can either be still concurrent or it can be truly parallel. Any questions on that? Okay. Okay, so the concurrent program is one thus that has multiple logical threads of control. We say logical because they may or may not run in parallel. A parallel program will then have the ability to execute multiple computations simultaneously, and it may or may not have more than one logical thread of control. Now this is where it gets a little bit weird. You can have something that's called data parallelism, in which you still have just a single thread of control, but multiple things are happening at once, and I'll talk about that in a minute. But our textbook here, and this is from chapter 1 of the textbook, has an alternative way of thinking about everything I've presented so far, which is that concurrency is part of the problem domain. When you look out in the world and you're modeling the problem that you need to solve, the real world has multiple things that can happen at the same time. So if you're trying to track that in a software system, you're going to want to have multiple threads that represent that possibility. You can do that in a concurrent way, and then you might be able to, in the solution side, get it in the right runtime or the right language that will allow you to also use parallelism when you're executing your program in response. So we can design a program such that computations occur simultaneously. That's a technique we have in our solution side of the thing. The concurrency will often come from the problem domain. Okay, so now repetition is good. So here is what I just said graphically. So here's a sequential program in a single thread of control. We have one machine, one process. It has some data code, and it has one thread. There's your single process, single threaded code. If you just add a thread, you now have a multiple thread, single process, single machine instance of a process. And here, this can either be concurrent or it could be parallel depending on the machine or depending on your runtime environment. And that's what I say here. Is it truly parallel? We have multiple threads, but we may not have events occurring in parallel, and that's because it depends on the machine. Okay, so now you could go to having single-threaded programs, but have multiple processes. And this is another way to get concurrency. So when you're writing your code, you only ever write a single-threaded program. And then what you're doing is having them do operating system communication between processes and allowing multiple processes to run at once and get your concurrency that way. Basically, if you take that approach, your application launches multiple processes, and then you're just letting the operating system take care of concurrency for you. It'll either run those processes in parallel or simulate concurrency, depending on what it's able to provide. And now, of course, I'm just showing, because of the space I have on the slide, just 2 threads. But you can have way more threads per process, typically hundreds or thousands of processes. And if you're using a language that we see later on this semester called Elixir, it's not quite the same thing. But Elixir has an overloaded term called process, and it's capable of running millions of those processes in a single operating system process. All right, and you can have multi-everything. You have multiple machines with multiple processes, each of those processes having multiple threads. Right? And you as a designer get to say, how am I going to solve my problem? And you have this whole range of options in terms of the architecture that you eventually create. So in fact, applications are dead, long-live applications. This is what applications used to be, single-threaded, single process. You double-clicked on something in the Finder or the Windows Explorer, and up popped one thing, and that was your application. Right? And now you can have applications that look like this. You have one multi-threaded process over here on this machine. It talks to another single process thing that is multiple-threaded. And then that thing talks to just this huge cluster of machines to go do things in parallel. And actually, to be more accurate, I really should show multiple of these here, because I kind of tongue-in-cheek say, for instance, we might call this Google. Right? So this is your web browser right here. This is the load balancer that takes requests at google.com, and then it's balancing those requests across thousands of machines that are either responding to the request or indexing the internet. And so now we refer to this whole thing as an application. This is the Google search application. Hundreds of components that all are deployed across hundreds of machines or thousands of machines, and they all have to be maintained and work together in order for you to type your first few characters and have your suggestions pop up. I mean, it's still stunning to me, and I'm used to I saw the web boot up, that we can do these sorts of things. Okay, now, just to put a little bit more, our book talks about the different ways that on a modern machine you can have parallelism just built right into what you're doing. So within a single machine, there are many levels of parallelism that might or might not have impact on the concurrent systems, depending on how they pierce the abstractions we've layered on top. So there's bit-level parallelism. So a 32-bit computer can do operations on 32-bit numbers way faster than an 8-bit computer can. Right? So you load up 2 numbers into registers that are 32 bits. On a 32-bit computer, if you say add, it's 1 instruction, you get your result. On an 8-bit computer, it's got to take the 32-bit number, put it into 4 chunks, load those up, process them, take the next one, process. A lot more work. You can't do it in parallel. At the very lowest level, depending on how many bits you can process, you can do those things in parallel. You can have instruction-level parallelism, where you have processor techniques like pipelining or out-of-order execution or speculative execution. And these are all things I'm not qualified to talk about. They're all several layers down in abstraction for me. But basically, one of the things I can, the speculative execution is something that you've got a sequence of instructions that your program is about to execute. And the processor is actually looking at that sequence, jumping ahead by, say, thousands of instructions, and noticing that there are places where there are branches, if statements. And what the speculative execution will do is it'll say, oh, let's pretend that the if statement is true. If it is, I'll just go and execute the true branch. And I'll execute it while I'm still up here, technically, executing where I'm at in the program. And then if I get to the true branch, if I get to the branch and it is true, well, I've already executed the true branch, I can just jump right ahead. That's basically what it is at a very high level. If it's not, if it turns out that the true branch, the if statement evaluates false, well then you got to throw away the work and actually execute the false branch. But your processor, the CPU, is doing all sorts of things to try to speed things up, jumping ahead, executing things in parallel, and then eventually hitting a sync point where it's got to say, oh, my speculation was wrong, I've got to jump back, or my speculation was right, and I just made things 10 times faster by doing it. Now here's where you can get single-threaded control, but multiple things happening at once, and it goes back to those GPUs, the graphical processing units. It's called data parallelism, where you load up an image, and you hear all the bytes in that image, and you say, take this transformation, blur them all, or add saturation, whatever graphical operation you want to imagine, but do it in parallel. So one instruction affects all of the bits in a single row of the image, and then you do the next row and the next row and the next row, and it's processing those rows in the image in nanoseconds and can significantly speed that up. But the program that's controlling that is single-threaded. It's just telling you, go do this operation, and a million operations happen at once. So the parallelism occurs on the processing as opposed to in the thread of control. And then finally, the thing that we normally talk about when we say this is a multi-threaded system are task-level parallelism. There's multiple tasks the program needs to do right now, and we've got them farmed out on a number of cores, and the cores are executing them simultaneously. And at some point, we sync up as to what's going on, and we do the next thing that we need to do. And these task-level parallelism will have multiple threads of control executing simultaneously under some particular memory model. So in Java, for instance, in a single process with all threads have they share memory. They have the ability to touch the same bits of memory. Not all parallelism systems will allow that. So some will say, oh, you can have multiple threads, as many threads as you want. None of them can share memory. Right? So there are different memory models that can go on. The ones that cause a lot of the problems, race conditions, etc., those are the ones where you have threads that share memory. So we'll look at that. Okay, so now, with all that as background, especially that whole thing leading up to Google, the Google architecture, imagine you coming into some new situation where a problem is being described about tons of data that needs to be processed, answers to be produced, websites to, web apps to stand up, or mobile apps also. You've got to sit down and think about how many machines are we going to need to pull this off, what components go on each machine, and for every one of those components, does it need concurrency? Sometimes you don't need concurrency. You can do single processing very quickly. If so, how will we achieve that concurrency? Will we have multiple single-threaded processes, or will we have multiple processes with multiple threads, or both, some combination? It's up to you. There's no right answer. You have lots of choices to make as you go into your design. So consider Chrome. Web browsers have been multi-threaded for a long time. So if you bring up a web page and it shows you the text, but images are slowly but surely being filled in after the text was displayed, that's multiple threads, right? So single process, but multiple threads, loading up all those images while still being able to be responsive and display the page to the user. But in 2008, Google came out with Chrome and said, this is a new browser that's also multi-process. So you double-click it, up comes a window, and in that window there's a tab, and for that tab there is one process that's been created. As soon as I create a new tab, a new process is created. And for every tab that I say Command-T for, again, another operating system process is being created. Now, each one of those processes is multi-threaded, so it can do the display of images and all that kind of stuff and be responsive in the tab. But now this is an application that spans multiple processes. And they still have their comic book that they released to explain the design decisions behind Chrome at this URL. So some of the advantages that they cite for this multi-process design is stability. So with single-process browsers, if something bad happens in one tab, it can crash the whole browser. So you had one tab that had some weird malware or whatever on it, and it brought the whole thing down. You lost all your work on all the other tabs. In this case, you've got that happens in one process. That process explodes. The tab disappears because the supervisor process notices the process goes away, but all your other tabs unaffected. Speed. With multiple processes, you can turn to the operating system for your parallelism. Let it optimize how it's going to use the cores. And then security. If you've got a JavaScript exploit or some other security exploit that tries to, from one window, attack the information that was stored in another window, you can't do that now. The other window is in another process. It's much harder to get across that process boundary than it is when you're in a single process. And so I don't have time to show it, but normally this is when I pop up Chrome and I show the activity monitor. But if you just bring Chrome up and it has one tab, and you bring up your activity monitor, you'll see Google Chrome, and that's the supervisor process. That's the one that loads the UI, at least the initial UI. And it's the one that keeps tabs of who are my children processes. But then it spins up a bunch of these Google Chrome helper processes. And what it does is, even with one tab, it has like 5 of these Google Chrome helper processes created. And that's so when you hit Command T, it can instantly use one of the previously spun up processes, because process creation is a slow thing. So it spins up 5 of them, it only uses one of them, and then as you add the first 4 tabs, you get those right away. And then what's happening is that as soon as you create a new tab, it tells the operating system, create me a few more of these Google Chrome helpers. So this here, I did this screenshot this morning, and this is with 7 tabs opened once it launched. So it had 7 tabs, it needed 7 of those Google Chrome helpers for each of the tabs, and it spun up 5 more, just waiting for me to open another tab. So this is multi-process design. It's a single app that has multiple processes communicating among each other, and we've got something that's deciding how many of these things do I need, monitoring for them to go away, all that kind of stuff. And because the operating system, by default, can handle parallelism across multiple processes, it just gets that for free. And then each process has multiple threads. It also depends on the operating system for those things to run in parallel as well. So it can get quite complex. But there's lots of other interesting benefits to multi-process design. One is that there are a ton of already existing oh, yes, question.
Could you say a downside of this multi-process thing is it's really CPU and memory intensive, and that's like an issue that Chrome has been dealing with, I guess?
Oh, sure. Yes, so it is, depending on how, like, this design, there are people who have thousands of browser tabs. So every one of those tabs is, at least in the simple implementation of that design, every one of those tabs is another process. And yes, if you have too many processes on a machine, that can slow the machine down, keep its fans running, increase energy consumption, all that kind of thing. What I suspect they do today is they'll have least recently used algorithms about which tab corresponds to an actual process. And if you haven't touched some of the tabs in days, those processes don't exist. So I assume they're going to be doing those types of techniques. But yes, you have a trade-off. So in fact, there was one time I was exploring, should I use multiple threads or multiple processes, and when for a particular program. And I mistyped the number of processes that I wanted on each increment, and I destroyed the machine. Took the whole machine down, had to reboot it to get it back under control. So if you spawn too many processes too quickly, the operating system gives up. It can have kernel panics and the like. Yes?
Don't most of those processes, though, spend most of their time blocked?
Yes, a lot of processes get blocked, but you've got things where you have JavaScript code that wakes up and makes an AJAX request. You've got it's blocked while the AJAX request is waiting, but then things come, streamed to it. So they could be at a low level of activity, not a huge level of activity, but still a low level. But yes, if you design it correctly, you can have a multi-threaded system, and if it's not doing anything, it's got 0 utilization. That's correct. So there's going to be trade-offs and balances there. But the potential for abuse is there, for sure, and the potential for getting it right is also very high. So what this page is, this comes from this book that I got the scattered application from. It's called Cocoa Programming for Mac OS X. It's the previous edition, but it carries over to the 5th edition, which is that in multi-process design, you can say, wow, I don't need to create my own search application. Unix, which is for the Mac, is the underpinning layer. It already has a find application. It has sed. It has awk. It has all these command line tools that have been around for decades and have well burned in, well understood behavior. I don't have to re-implement that functionality. I can just spin up a process where the process invokes sed or awk or whatever I want and just wait for the output to come back, and then I process the output. So a multi-process tool could actually, you don't have to think of them as long running, they could just be very short, but then you invoke whatever you want in that process and wait for the output to come back. So that's one thing you get to start playing with multi-process design. Another one is that if there is something you use and it has a memory leak, it's not your memory leak. So as soon as you're done with invoking this other process and getting its data back, you can tell it to go away. And then that memory leak, if it occurs, is not part of your program. It's something that the operating system will take care of. And then you get a bunch of flexibility. Like Photoshop has a well-defined API that you can plug things into. And you have flexibility in what language you want to write your plugin for. Now in Photoshop, you probably want it to be in C, so it's fast. But not necessarily the case. You could, as long as you could have development environments in other languages that target the binary format for those plugins and be free to do anything you want in those plugins for how you code up your code. They're just going to call it as an external process and get back the data. So you get a lot of flexibility about the types of languages you can bring into a system. It doesn't all have to be the same language. It doesn't even have to run on the same machine. So this multi-process approach gives you lots of flexibility. All right, and then for setting aside multi-process design, if we think about multiple thread design, then as we already saw with the scattered application, you can use threads to make applications more responsive so that they are always able to respond to user input, even if it's doing something in the background. And you can use the threads to make applications faster when it's doing either computationally intensive apps, compute-bound, or data processing apps, which are I/O-bound. And there are actually different strategies for those two types of apps that we'll get into over the semester. Okay, so let's look at some of these dangers to close out this lecture. The first danger of having multiple threads in your software system design is that you can suffer what's called starvation. And starvation means that none of your threads are blocked. They all are running and they're doing something. But for whatever reason, they're not overall, in terms of the overall progress of what the user is expecting the system to do, it's not making progress. And so we call that, in those cases, we call that threads being starved. They could be doing something, but for whatever reason, our system is running other threads that's not allowing the work threads to go forward. As one example for this, in early versions of Java, you could have multiple threads, and it could be cruising along, but all of a sudden the garbage collector kicks in. And the garbage collector kicks in, and every other thread is stopped, and it goes and cleans up memory, and then lets go, and everyone starts up again. And in those situations, yeah, they slowed down or they stopped for a little bit, but they weren't doing much. They were maybe making a bit of progress on their instructions, but not much while the garbage collector came in and cleaned up memory. So that was just an example. You had no control. You had very little control, I should say. You had some control, but very little control about when that garbage collector would run. You had no control over the impact it would have on your application. You could see noticeable pauses when the garbage collector came in. They've gotten much better. The garbage collector's design has changed to be way more efficient and not to block the system that way. But that's just an example. The generic solution for this problem is you've got something, a thread A that is doing something, but thread A is starving the other threads. You have it time out every now and then and just stop working. So that's one approach you can. The other is to make sure that in all your threads you have the option to decide, I'm going, you know what, in this particular state I can let go and tell the scheduler run something else. And in those, the low-level thread APIs, that's the yield call. You can just say, I yield, and that means, suspend me for a little bit, let something else run. And that's kind of the generic solution for starvation. Almost at the high level, almost every one of these problems requires some sort of redesign. I can't spin up these threads this way. I can't have them interact this way. But in general, you can have timeouts help with starvation. Deadlock is when you have two threads, and they're each waiting for a resource that some other thread has. So thread A is waiting for B to give up resource C, and thread B has resource C, but is also waiting for resource D. And if you want to know what resource could be, it could be a printer, it could be a network connection, it could be read the same file. We're being very generic about what the resource is. But B has it, and A wants it. And A, meanwhile, is holding on to resource D, which is what B is waiting for. So they each have one resource waiting for the other, and they're not planning on giving up the resource they have until they get the other one. Right? In that situation, they are blocked, and they will never be unblocked. That's a Control-C situation, unfortunately. The generic solution is you never have A go for D and B go for C. They both have to go for D. That's the generic solution, because then one of them is going to get it, and the other has to wait for D to be available. And now that one of them has D, they can go get C, they've got everything they need, they run, they let go, and now the other thread gets D, gets C, and goes from there. So deadlock is insidious sometimes in how that creeps into a system, but once you're aware that, oh, yeah, the way I set things up, there's a chain here of dependencies, all I have to do is have them not grab things out of order. So they all have to get the first resource, then the second resource, then the third. And then you can get deadlock to go away pretty quickly. And then the insidious ones, the ones that will have you questioning your sanity, the ones that will have you up late at night because you run it 100 times, you don't see it, then you go get a drink, and on that 101st one it happens, are these race conditions. And so you have two threads, they both access the same resource, but there's no protection on the resource. So they both come in, and I'll show you an example where they both look at a value, and they both read it, and they both do something with that value to compute a new value, and then they both try to set the value. And so when they do that, the last thread wins, right? I saw it was 5, I computed 10, I'm about to put 10, I do put 10 in there. I put 10 in there. Immediately someone else also saw 5, had computed 11, and there was nothing protecting this, so they wrote 11 when I had just written 10, and they should have known about that. So we'll see an example here in a minute. Anyway, it's very easy for threads that have access to the same variable or the same memory to get the state to be completely inconsistent, and then your system goes off the rails. You can also get into problems even when one thread is doing just the writing and the other is doing just the reading. If you don't synchronize it properly, you can get stale reads where it's reading the wrong value because the latest value just didn't propagate through the memory model to the thread that's doing the reading. All right, so let's see some examples of this. The first example of race condition is I have two threads, A and B, and they both have access to an integer variable C. And what happens is that we're going to increment this value using C equals C plus 1. And actually in the code it just says C plus plus, right? So increment C. Or you could even have C plus equals 1. Now the problem we get into as humans, we look at that and we go, oh, that's atomic. We're just going to take the value of C, add 1 to it, and stick it in as the new value. But the problem is that you can, at threaded code, the instructions for C equals C plus 1 get split. So if you want to think of it as in Java, there are multiple byte codes that get generated for the C equals C plus 1 statement to be executed. And so it's what's called not atomic. And so you can have situations where thread A and thread B come in, and they both read C at the same time, and then thread B gets blocked, and then A increments by 1 and writes, and then B becomes unblocked. It's already done its read, so it doesn't read again. It increments and writes, and now we've got an inconsistent state. It should have been, if we started at 0, it should have been 2, but we left with 1 as the value. And I'll see that right now. So here is a program I wrote. Let me see here. Go into race condition. Let's make sure this is big enough for you to see. Okay, so we're going to look at just this one for right now, which is test simulated. And what this program does, this is a Java program. We have our public int count. That variable right here is the thing that our threads are going to be sharing. Count starts out with the value 0. And then what this code does at a very high level, and I'll release this code so you can take a look at it, is it has a thread array. So this is an array of 10 thread objects. And what we do is we loop 1 to 10, and we create a new thread. So here I'm saying threads I, which is assigning into that variable a new thread. To create a thread, I can create an instance of runnable. I have inside of that runnable a random number generator and also a method called run. And the first thing I do is I generate a random number, which you'll see in just a minute here as to why we did that. I'm instantiating my random number generator. And then each thread is going to loop 3 times. And here's what it does. It reads the count variable. So into a local variable, temp, it says, what is the count, current count? And it prints that out. I have read this value. Then it sleeps for a random number of milliseconds, up to 300 milliseconds. And then it increments. It says t.count should equal temp plus 1. So there's the write. I have the read, I have a pause, and then I have a write. And I'm doing all of this. I don't actually have t.count plus equal 1 because I'm trying to make it so that the threads get interrupted, right? So I want to create a situation where thread A is going to come in, read the value, and then get blocked. And then thread B comes in after it. Okay? So that's the basic notion. Then down here what we do is we loop through the thread array. All that did was create the thread. They didn't start running. So then we have to loop through the thread array and say start. And then we loop through the thread array again and call join on each thread. So that's going to make us wait for every thread to be done. And then we finally end by printing out what the final value of count was. So with 10 threads and 3 increments, that should be 30. When we run it, test simulated, class path, build, test simulated. When we run it, you'll see our count is 3. You see that? Final value is 3. It should have been 30, and it was 3. So what was happening was, as we can see all throughout, 10 threads popped up, and the first thing they did was read the value. What was the value? 0. They all got 0. So then down here, as we're going along, we're going to see I'm writing 1, I'm writing 1, I'm writing 1, I'm writing 1, I'm writing 1. We got 10 writes of the value 1. And then the threads that wrote 1 are starting to read again, and they get the value 1. But here's a case where someone wrote 2, but someone else had read 1, or up here had read 0 and is still going to write 1 and write 0. There's just no protection on this variable, and everyone was reading out of order, and so we ended up with the highest value ever getting to was 3. Now, there's another program I have here called test hidden, and that just refers to the fact that all I'm doing here is using the ++ operator. So here I say the thread is writing ++ t.count, right? So that ++ operator says increment by 1. And to us looking at it, it looks like that, hey, that should be atomic. That should just happen. But it does exactly the code I wrote in test simulated. It has to read, it has to increment, it has to write. So it's not atomic at that level. Now what happens here is if you just run this with, if you run it, go back up here real quick. If you just run test hidden with 1 thread, no problem. It gets to 3, not a problem. If you run it with 10 threads, no problem. T.count equals 30. Yeah, nothing's wrong here. How about 100 threads? Nope, T.count equals 300. That's perfect. There's no, 299. I was just about to say there's no bug here. Let's do 1,000 threads. 2998. So there were 2 times where even with that ++ we got a race condition. And here's one with 10,000 threads. 29994, right? So very subtle. Most of the time it's reading and writing, no problem. Every now and then, 2 reads that stomp on each other. All right, we'll pick up there on Tuesday. Thank you.
Yeah.
These are theirs.